So we've been talking about radioactivity and the different types. We've also looked at Rutherford and how he discovered the different types of radioactivity. In this lesson, we're going to look at the nuclear reactions, or the reactions that occur as a element or an atom undergoes one of these decay processes. The first thing we need to look at is the fact that when we are doing nuclear reactions, we're going to use symbols that include numbers that you normally wouldn't find in a normal chemical reaction. We're going to have the element symbol. To the upper left, we are going to have the nuclear mass, which would be simply the total mass of the protons and neutrons. But sometimes we'll see the value of 0 because for an electron, or for those particles that have no mass, like the proton and neutron do, they will be designated as 0. At the lower left, we will have a nuclear charge. In this case, most of the time we consider these the atomic number, how many protons. But again, we will see some particles have a charge associated with them, and that is going to be designated down there at the lower left. The first decay we're going to look at is an alpha emission. We know that an alpha particle is made up of a helium nucleus. It has a mass, its nuclear mass is 4 because it consists of 2 protons and 2 neutrons. At the lower left, we see it's got a nuclear charge of 2 because of the 2 protons. Beta emission is basically an electron that's being kicked out of the nucleus. There's a lot more going on than what we're describing here that's taking place in the nucleus, but understand that this electron is being ejected from the nucleus as part of our nuclear decay. The symbol is E for electron. To the upper left, we have a mass of 0. And that's because the mass of the electron is so much smaller than the mass of protons and neutrons that we essentially are calling it a mass of 0. Electrons do have mass, it's just not very much. At the lower left, we have a nuclear charge of -1. Basically, it has the exact opposite charge of a proton. Now, the next type of nuclear decay is called a positron emission. And we haven't talked about positrons. They are a special type of subatomic particle. They are also called an anti-electron because they have all the properties of the electron except they're exactly the opposite. In this case, their mass is still 0, but the charge is +1. And for gamma emissions, we don't have any particles associated with them, so we're not going to include those as part of our reactions. Some general rules for our nuclear equations. One, the total mass number must be the same at the beginning and end of the process. So that number in the upper left-hand corner, which tells us the mass number of the particle, all of the particles on the reactant side, their mass must total the same mass as all the particles on the product side. If we have in the atomic charge follows the same basic principle. The total charge, nuclear charge on the reactant side must total the total nuclear charge of the products on the product side of the reaction. So let's take a look at some of these reactions and see how this is put into place. Again, we'll take the first as an alpha decay. Uranium-235 is the primary ingredient in nuclear or older nuclear weapons and what we use today in nuclear power plants. This undergoes an alpha decay, and when it undergoes an alpha decay, it is going to produce a helium nucleus, the alpha particle. Notice here we've got the superscript of 4 for the helium and the subscript of 2. Based on the previous statement is that we have to make sure that all of these numbers add up. The other product as part of this decay process, what's left behind after the helium nucleus is ejected from the uranium nucleus, is we end up with thorium with a mass number of 231 and an atomic number of 90. That's because the uranium has lost 2 protons to make it thorium, and it has lost a total of a mass of 4, 2 protons and 2 neutrons, so our mass number or atomic mass is mass number or nuclear mass is 231. So the product side, 231 plus 4 equals 235, which equals the nuclear mass on the reactant side. Same thing with the atomic charge. The 90 plus 2 equals 92, which equals the uranium on the reactant side. In our beta decay, very similar situation. We've got strontium 90. It undergoes a beta decay process, and in the process ejects an electron from the nucleus. Based on this information, we'll see that the element that's left behind is going to also have a mass of the nucleus of 90 because we haven't changed that mass. The total number of protons and neutrons is the same. The difference is that we have more protons than we have neutrons in the original strontium. When the electron gets ejected out of the nucleus, you can think of that as turning a neutron, which is neutral, into a proton, leaving behind the positive charge for the proton and ejecting the negative charge from the electron. Again, the total amounts add up on both sides. We have 90 for a nuclear mass on the reactant side. We have a total of 90 for the nuclear mass on the product side. We have 38 for the atomic charge on the reactant side. We have 38 total for the atomic charge on the product side. And the last one is the positron emission or positron decay. And again, same format. Fluorine 18 undergoes a positron decay or positron emission, and in the process ejects that positron, which has a mass of 0 and a nuclear charge of +1. That means that our other product must have 8 protons so that our nuclear masses and our nuclear charges add up. We start off with a nuclear mass of 18 on the reactant side. We end up with a total nuclear mass of 0 plus 18, which is equal to 18 on the product side. We start off with an atomic charge of 9 on the reactant side. We start off with a total nuclear charge of +1, or 1 plus 8, which is a total of 9 on our product side. So when talking about these nuclear decays, the basic process is fairly simple. The different particles get ejected from the nucleus, leaving behind an element, a new element, with a different number of protons and possibly a different mass number, but the total of both sides must be the same.